doesn't want to move again or leave Zach.
Yeah, why not? He just moved him on this semester.
Yeah, but plenty of people told me that he was not planning to live with Zach anymore. But that changed recently.
So I didn't take prepared ahead forms for little, how to say, quiz exercise. You need two pages.
Fine.
It's not for a big contribution to grades, but it is for better perception of the material. So I invite you to write something, not your notes, but there will be a couple of assignments for, how to say, self-test, so that you follow and can derive something. Do not panic, and you do not have weaknesses even if you fail. So today is, I wouldn't say all meetings are important, all are complicated, but today is in some sense special meeting. It is unique in this sense. Today is one of, or maybe even the only one time when we speak literally about observables. And when you write papers with computational component, the equations that we will cover today are, well, at least one of them is to write literally, even if your expected audience knows about what you do. So there will be something related to real world, not the actual theory, but real world. In fact, we will have three components. First, we will quickly recall back what is Hartree-Fock theory, although we're starting a new chapter. We're going to this functional theory, but today is kind of a bridge in between. Second, we will review interaction between light and matter, and there will be observable related to UV visible spectrum. It is in simple writing, the final equation will be very evident, but it is not clear where it comes from, and you will grow inside yourself if you take note or try to derive it with me. So, and I will also make a little review of materials that Christian has presented on his presentation, Koopman's theorem, and then there will be at the end very important concept that will set up a compass for our next month: the principles for modeling periodic materials. So in addition to chemical molecules, which is each molecule is like isolated object that may collide, may move, there are solids, nanostructures or just big solids, and we cannot live without them. Even if you have chemical molecules, all your equipment is made of solids. It interfaces surfaces, tips, electrodes, and description of solids has some specifics, which is not a part of standard chemical modeling. Okay, more or less clear. So yeah, starting the third chapter, and on the lab tomorrow we will start practical steps towards modeling solids with new software, not Gaussian. Okay, I will mumble something about Hartree-Fock, but you kind of know it. So a little nomenclature. If you read literature or notes prepared by developers of Gaussian, you will see that they use the term density matrix. And typically, this term is not from Hartree-Fock theory. It is the invention to use this concept in explaining Hartree-Fock. So, if you do standard things as we discussed in class, we can formulate Fock operator, and then we need matrix elements of Fock operator in basis of molecular orbitals. But practically, one may find matrix elements of Fock operators in atomic orbitals and then convert it from atomic to molecular through some transformations. So the connection between molecular orbitals and atomic, the distribution, the expansion coefficients squared, so to say, or products of expansion coefficients of molecular orbitals over atomic orbitals can enter directly into the Fock matrix, which has this Coulomb exchange and standard things. So if you express matrix elements of Coulomb exchange in atomic basis, then in order to get total energy, or in order to get Fock matrix, you may put here expansion of molecular orbitals over atomic orbitals. And in context of Hartree-Fock theory, one calls it density matrix. So we will never use it from now on. It is only if you feel confused reading papers or literature related to Gaussian software. We will use concept of density matrix, but in very, very different sense and context. Okay, so you are invited to take a piece of paper and try to fill something. This something is a flow chart of how Hartree-Fock algorithm works. And it doesn't matter how many steps you have here. So this intermediate boxes in flow chart can be put in one big box or two big boxes. But the main idea is that as the result, so please try to do it independently. To saving time, I will start. I will start doing it right away. So the goal is to get total energy that includes everything, and we report, not we, the software. So please try to fill the flow chart to your best understanding. I will even not look on it, but for yourself it will be pleasant and useful exercise. So who told about number of electronic steps in on the last presentation, making them from 130 to 500? Vijay. Okay, so you know that there is an iteration cycle, and it breaks if the precision criterion is satisfied or if it hits a limit. So if the total energy at step I is minus total energy at step I minus 1 is smaller than tolerance limit, then we stop computation and report total energy. So Hartree-Fock theory is the tool to compute total energy. All other things are auxiliary. And we start from positions of ions. So R sub I, the position of ion number I. Ion number I capital. And we also put in the tolerance limit, which tells smaller than smaller than epsilon tolerance. So right now we look on the Hartree-Fock as the black box. We start with position of atoms. The tolerance limit is hidden somewhere in software, and as a result, you get total energy. In addition, you do get energies of orbitals and shapes of orbitals, but they are just for your chemical intuition. Neither Hartree nor Fock promised that the orbitals will be available. Okay, then there is an initial guess, which can be random or based on chemical intuition, guess of molecular orbitals, which can be just as expansion of each orbital number I over atomic orbital U. So one needs some random, no matter which, reasonable or unreasonable orbitals to start formulation of Fock matrix. Matrix. And one needs orbitals because one populates all but one orbitals and they create the background Coulomb interaction with the last element. So orbitals are needed for background. O for background. Then upon you do have your Fock matrix and you do have FAT for matrix. F times C equals epsilon. S FAT S times C, which is Fock equation, right? So Fock matrix times vector of expansion of molecular over atomic. C expansion of MO over AO. So this is eigenvalue problem that you can solve, and then based on mu molecular orbitals, mu C molecular orbitals, one can find total energy. Energy total mu. And then one compares the new and old total energy, and if it was good, it reports the answer. If not, the molecular orbitals that were found here are fed into reformulating Fock matrix, and then it is diagonalized again, and then the procedure repeats until success. Okay. Why do we do it? Since we are not going to use Hartley-Fock anymore. In about 3 weeks, we will have very similar flow chart with density functional theory, which is a very reliable workhorse for any computations. So there will be things that we will repeat and mention in papers and use in the research, and it will be a little bit different, but following similar ideology. Input, output, total energy, and the procedure inside will be different in equations, but similar in the self-consistency content. Yes?
So when it doesn't find the correct total energy, it goes back and repeats. So like with the perovskites, when you get a failure termination, is that because we don't do enough steps to find that point, or is that something else?
If you do open shell, then sometimes it may fail. There is no theorem that it will convert all the time. For example, if there are two degenerate or nearly degenerate electronic states with very similar but not equal expansion coefficients, system will not know which one is better and flip between them infinitely. First, second, and it may go to infinity.
Okay.
So if one with the degeneracy by additional interaction, like if one includes spin orbit that will lift any degeneracy, then it will converge. But spin orbit is not by today is in Gaussian.
Okay.
There are some problems and they can be solved, but not always they are solved immediately. Okay. Let's check if I did reasonable work compared to last year's. So you call it self-consistent field because this background field by rest of Pelton's agrees with itself. So what comes out and what comes in should be the same. So it's self-consistent, consistent with itself. And I even placed the detailed equations that will be distributed to everyone if by some reason you need it. Okay. So observables. It is our goal, and it is goal of any research. Main way to probe properties of molecules and solids is probe them with electromagnetic radiation. Nuclear magnetic resonance is radio frequency, infrared spectroscopy, same electromagnetic, UV visible, X-ray. All characterization primarily is electromagnetic probing of the sample. I'm not sure if anyone does acoustic probing or gravitational probing. I don't know, just you would fall and break. So mostly it's electromagnetic. And there are reactions, but it is properties to participate in reactions. It's not property of the sample itself. So electromagnetic radiation is universal probe. Universal probe. What is electromagnetic wave?
So a wave with like certain energy, frequency.
But if you look on it very microscopical, what does it mean? We have light, we have electromagnetic wave, or we have radio frequency.
You see like a periodic wave?
Periodic, yes, periodic wave, plane wave. But periodic wave of what? Yes, right. Electromagnetic field. Correct. So, what is electric field? It's an important skill to find answer to questions even if you do not know the answer. It's a reason that makes a charged particle to move, right? So if you have an electron and you apply electric field, it gives it an acceleration. And if it is, so it is static electric field. But in the light, it is not static, it's dynamic, it changes up and down or left and right. How are you? It's just empty papers, but you'll have a chance to practice some derivations. And maybe I will invite someone to do the work. What is light? Question to Daniel.
What is light?
Yes.
Like I guess a photon of energy.
Yeah, you are from the you're considering from the point of view as light as a particle.
Yes.
But at the same time, it is wave, right?
Yeah.
Wave of what?
Wave.
Wave of what?
You said wave, right?
Yes, but wave of what? It's not wave like of water on a.
Wave of vibration.
Vibration, same as wave, oscillation of some kind. But what does oscillate in electromagnetic? Be careful and philosophical. Electromagnetic, then something electric and something magnetic oscillates, right? So what electric?
It's what electric?
Field? You know, electric strength of electric field that makes electrons to move, right?
Yeah.
Good. And it oscillates. So there will be something that each of you can do, but since it is so simple, I want to do it myself. So if you have, I don't know what I would put here, maybe space. Z X Y Z. up and down, up and down. So the electric field, since it makes electrons to or charged particles to move somewhere, it is vector, right? So at each point of space, it makes electrons to move up or down. And one use letter E. And at the same time, due to Maxwell equations, which are favorite toys of people in physics, there is a magnetic field that would act on coils of electrons in which is often denoted by letter E. E of R and E of R in space. And it will be stable. Well, if you imagine such fields without any sources, without source of charge, it will not be stable. It can exist only if it moves. So changing of the electric field creates changing magnetic and vice versa. Traveling. So it has the period, the distance between two humps. And it has period frequency in space. So at each time it moves forward, and if you point one point of space, it will be oscillating. Right? This drawing moves forward, and selected point of space, it will oscillate. Right? You saw this picture. It's nothing too much new. So classically, it launches charges to move. But from quantum point of view, electric field, especially if it is oscillating electric field, it induces transition between electronic states. And we are going to focus on this aspect. Okay. I don't know when I was better drawer, but it seems similar. So how does the electric field changes electronic state? Just promotes up or down if it is in resonance with transition energy, right? So you have electronic states, and if it is in resonance, you will have a peak in the spectrum. From experimental point of view, from theoretical or computational point of view, any interaction is an additional term in Hamiltonian, right? How does Hamiltonian of interaction between electric field and charged, non-charged, and a molecule looks like? If it is charged, it is just moves along, constant acceleration. And if the molecule is neutral, balanced, how does it interact with?
Should move.
Huh?
It should move.
It shouldn't move. But if it is a polar molecule with a little plus and a little minus, and field will go at some angle, will the molecule be happy? So we have from plus to minus vector mu, and here we have vector e. So the molecule will not be happy. And it will not be happy until it rotates to stay collinear. Right?
Oh, so like NMR kind of thing?
Well, it is everywhere. Same as, well, in analog with magnetic, it is compass that wants to rotate. And same with electric field. If you have electric dipole and you have electric field, it will do something until it is, unless it is parallel and goes along. So here the dot is color product. So if they are not collinear, or if they are opposite directions, it will be increase in energy. If they are along each other and parallel, it will stabilize the overall system, the electric field plus dipole. And there are more complicated and rich terms if you want to be super precise, but this is sufficient for simple guys, for myself and yourself at the beginning. And if you talk to rigorous people, you tell that interaction between electromagnetic field and matter is taken into account in dipole approximation. In most practical aspects, it is sufficient if you do not do exotic things. So dipole, which is just charge times distance, scalar product is electric. So if you have two charges, plus q minus q and distance between them r, then dipole vector, if it is space, it's amount of charge times the vector that connects. How does it change if, well, typically molecules consist of more than two charges. Two charges will be only for hydrogen atom, proton and electron. Everything else has more complicated structure. But Z. So we have ions located at position r sub I, as we started our course with. And they have their positive charge. And we have electrons, which we can count from 1 to the number of electrons. And here we start just from number of ions. So all electrons have elementary charge E, and all ions have their charge number from periodic table times elementary charge. And if we formulate dipole in this way, then it will be an operator of dipole, general for multi-electron, many particle system. So dipole operator. So no matter 200 or 1,000 electrons, we did our job. Right? Positive, negative, and distance between them. Now, we do want to model situation when we have promotion of electron from one orbital to another one due to interaction with electromagnetic wave. So we already know that the electronic state in ground or excited is composed as Slater determinant of all molecular orbitals. Wave function is Slater determinant. We know that operator is just dipole. What else? And we know our procedure of if we want to characterize some process from quantum point of view, we typically need to find expectation value or matrix element of transition. So we can put the wave function initial before interaction, wave function final after interaction, and put operator in between. And if you compute such thing, it will characterize how efficient the process is. And if you want to give rates, we need to just make square of this with some additional factors. But it is very, very, very universal for anything. And we are going to practice it. So you are educated people, you know about Slater determinants. But I am a lazy person. I will die if we do exercise of writing slated determinants again and again for initial and final. So just as an illustration, I will use Hartley products. So leave behind anti-symmetry, and just as an example, use Hartley product. And also as an illustration, so that we do not get exhausted. We are not going to look on the general, but look only on a system of 2 electrons. Forget about spins, just 2 orbitals, 2 electrons, and by light we promote electron from orbital number 2 to orbital number 3. Okay? Just a little experiment. So ions are not moving in this experiment, so we nail them down and remove them from quantum operator. So our quantum dipole operator will be position of electron 1, position of electron 2. In ground state, our wave function will be for electron number 1, orbital number 1, for electron number 2, orbital number 2. Okay. If you have excited, then we keep electron number 1 in orbital number 1, and we move electron number 2 into orbital number 3. Okay? So it's still multi-electron wave function, but second electron jumped from second orbital to the third. And we do need to find matrix element of transition dipole between ground and excited state as ground dipole matrix element excited, or whatever, we can solve the order. So we are going to pursue this procedure. We are going to practice it and get some observations, some trends that will be really helpful for the rest of our life in the course and rest and remaining life in research if you do some. So it will be some valuable conclusions. So what do Dirac notations for bracket mean? How do we interpret them? Means we integrate over all degrees of freedom, right? If you have Bryant cat, if you are in the representation of discrete vectors, it will be a scalar product. This, and if operator is a matrix, then row by column, row vector matrix, and then column. And if it is continuous functions, then this Dirac notation will be just integration. For mu, we agreed it will be just R1 plus R2, right? Just definition of dipole. And elementary charge is 1 if we are in atomic units. And phi ground, again, I'm just repeating, it is phi 1 R1, phi 2 R2, and phi excited is phi 1 R1, phi 3 R2. So we're going to plug in these components into this expression and see what we will observe. So why are we doing this exercise? I'm not passionate enough to keep the intrigue, although it is very pleasant to do something boring. And surprise! There are so important results. Let me tell it right away. multi-electron wave functions are unnatural for humans. They are boring, exhausting, long, and we cannot speak every day and write products or Slater determinants. We understand that they exist and they are right concepts, but they're not for humans for giving all tiny detail. And it will be very pity if the observables will depend on all multi-electron degrees of freedom. With next about 5 minutes of derivation, we will prove that instead of multi-electronic wave functions, multi-electronic transition dipole, the ability of a molecule to absorb light will depend only on properties of the orbitals that are involved in actual transition. So we will reduce this only to the properties of the starting and ending orbital. So right now, our multi-electron wave function is pretty simple, just product of two, but it can be product of 300,000, very complicated. But if we prove, or at least show, that properties of interaction between light and matter depend only on the last orbital that is involved in actual transition, the life will be so much easier. We can get a lot of intuitive understanding of how molecules act in response to the light. So we can have a glance on orbitals and immediately tell which of the orbitals will give larger peak into spectrum. So you will be like kings of optical properties of molecules with the information that we are going to go through. So we want to reduce optical properties, or analysis of optical properties, to the one electron picture instead of multi-electron, if possible. Ground, excited, transition dipole. And actually, after we plug everything in, I used maybe a little different notation, but it is the same. So integral dr1, integral dr2, it is from Dirac notation. We also need to do the stars for the left for complex conjugate, dipole operator in between, and we need initial and final states. So first term we say, second term same independent variable but different orbit. Okay, so what I invite you to do and what I will try to do myself is to take the same expression, recognize it, right? Take a blank piece of paper and try to just derive it, to go forward. You can not listen to me and do it independently. And I will give comments and try to derive it myself. So there will be two features, two properties that I'm going to use. So first, if the operator is a summation, then this big integral can be split also into terms. First, where only one variable is used. Second, as a operator, and second term when only second variable is used. So split all integral onto two terms. Two integrals, two terms. Another property is that we assume that our orbitals are orthogonal. Orthogonal. So that integral over any variable can be 1, 2, or just r, phi I star r times phi j r will be 0 if I not equal j, will be 1 if I equal j, which means chronicle delta ij. So I'm going to use these two problems. So with this, the I'm just rewriting integral twice. First, integral dr1, integral dr2, phi 1 star phi 1 phi 2 star phi 2. Different colors we have. Times R1 phi 1 phi should be 3 here. It's very important. It's my type, but it should be 3. Otherwise, it will have no sense. Sorry for misleading you if you went too far in the relations. Phi 3 R2. Plus, there will be second term of the same nature, but with different variable. dr R1 dr2 phi 1 star R1 phi 2 star R2 times R2 So before I go forward, I may just sit for a second and analyze what I see. So both terms include integration over 2 variables. But if you look on the first term only, we can see that there is a group of terms that depends on the variable R1. Is first the operator and this second last. So they depend on R1. And there is another group of terms that depend on second variable, R2. So I can regroup this integration. So I can put everything that depends on R1 into here times integral of dr2 of everything that depends on R2. This and this into here, and this into integral of R1. So when I will go to the next slide, I will do it explicitly. But what do I expect from this operation? So in first term, there will be orbital, first order variable, and orbital again. In second term, there will be product of orbital number 2, orbital number 3, both depending on R2 integral, right? You follow? How does it relate to here? So it will be orbital number 2 and orbital number 3 integrated over the same variable. So different orbitals, they do not coincide. So it will be 0. And then we do not, it doesn't matter what will be here. We just do not need to take this, the first integral, because it will be 0 anyway. And similar trick can be applied, so first term will be 0. And then we need to process only the second integral. Please try to derive, because I'm mumbling something, you can be much quicker. If you look sharply, you can get answer. And if you do, just lift your hand and let me know. step back and write it. So, set it, new, ground equals first term is 0 plus second term, which is dr1 dr2 1 and just rewrite it. Start 5 2 second variable 2 1 minus 3 2. Now I can rearrange the terms. Everything that depends on R1 will go into first box, times everything that depends on R2 will go into the second box. So here I have 1 star R1 this time, 5 1 without star R1. This and this. And in the second box, I have 5 2 star 2 minus 3. So I'm processing the second. Yes, please.
Can you quickly explain again why the first area was 0 for the first?
What you're saying, explain it later. Clear?
Yeah.
Is it clear for everyone? Yes? So now I'm doing the second term. Which depends on R2. So all factors that depend on R1 go into the first box. All factors that depend on R2 go into the second box. So what do we see in the first box? Phi 1 R1, Phi 1 R1, right? You got it. What does it? What is equal to? If we practice the orthogonality,
Would be 1.
yes, orbital times itself integral will be 1. Delta 1 1. So we kind of cancel and tell that overall matrix element of mu between excited and ground equals only to the second factor. So orbital where we start from, orbital where we end from, depending on the integration variable. And since we integrate over this variable, it doesn't matter how we call it. We can call it W or something exotic. It doesn't matter. It disappears after integration. So independent variable, independent variable, independent variable, integral, different orbitals. So probably I will wrap it up in different terms, but the idea is here. For the multi-electron function, ability of a molecule to interact with light depends on the one electron matrix element between original and final orbitals involved in the transition. Right? So one quantum, one photon induced transition from one orbital to another. One photon, one transition. And what can we see? If the orbitals are phi 1, or phi 2 and phi 3. So if the molecule is big something, but the orbitals are localized in different spatial areas. If they do not overlap, then the matrix element of interaction with light will be 0, right? So you can look on two orbitals, like HOMO and LUMO, and if you see that they are offset by space too far, you can tell this will be a dark state. It will not participate in any optical activity without doing any spectrum, just from orbitals. So they need at least to share some overlap region. To share, and this is important property. So we got that first disappears, this gets into 1, and this the only matter. Same idea. Orbital 2 times orbital 3. So multi-electron observables can be represented in terms of 1 electron matrix elements. Even if you do have advanced computer code that does matrix elements in many electron bases, sometimes you can do something very quick analysis yourself based on this problem. So you can intuitively analyze and predict properties of materials with the skills that you have now. Even if you stop course right now, you already can do something really valuable for interpreting experiment. Enough. I think I was trying to repeat it again and again. Okay, so I didn't show the Koopmans. I will show it at the end. I will not forget Christian and Koopmans and the theorem. But you don't need to live literally at noon. You have a lot of time, right? Okay, so we are starting very new chapter. If you were exposed to physics research or physics courses, it will be not so challenging. But if for all your life before now you were doing only molecules, it will be, you all will do it. It's not challenging for intellectual abilities, but it will be new. You need to reorient way you think. So crystals, what are they? From microscopic point of view.
An organized arrangement of molecules.
Organized, yes. It means that you can take a small fraction that repeats again and again. And it is a main purpose why crystals structure can be determined through X-ray diffraction. So if you have, again, I'm not going to something rigorous. If you have pattern, a small unit that consists of 2 atoms, for example, silicon that used in semiconductors, or graphene, 2-dimensional graphene, can be cast in terms of just unit cells, 2 elements. But sometimes for many realistic crystals, you have more, but it's only an example. So if you go away from this to up, down, or side, you have the same pairs of atoms, 2 here and there. But it doesn't mean that in your atomistic model you need to have all of them. If you take into account interaction with neighbors that are over the wall, you can practice very small models. You just need to take into account the interaction with replicas. What are the, how do we treat this system? So first, we do have positions of these atoms by distance from origin, right? And then you do have size of your unit cell, let's call it vector A. So if you add vector A to position of each of these atoms, you get 2 new vectors, R1 plus A, R2 plus A. So this will be positions of your replicas in new periodic model. So this doesn't sound offensive to you. If you go to the next one, you have R1 plus 2A, vector addition. Okay? R2 plus 2A. Or minus, you can go up and down. I don't know how to smartly describe it, but if you've got the idea, you don't need it. Just adding the unit cell vector, several times, you can get coordinates of atoms of ions in each replicas of the model. Okay? Practically, let me focus. I'm jumping too far ahead, but let me focus your attention right now. If you take the last atom in first replica, and first atom in second replica, there is an offset, there is an empty space, vacuum between them. You need to leave space that allows some empty space for chemical bond. If you do not leave, if you want to smash them into each other, it may lead to atoms from one replica to another replica to smash into each other and give infinitely high energy and explode everything. Well, computational explosion is not dangerous, but it will be unrealistic. This will be main message of Wednesday lab. So we will learn how to add vacuum in a wise way for the models. So if you go from one cell to next cell, we just add to all positions the translation vector. And if you are moving by so many, 1, 2, 3, several integer number of units, atoms will be the same, their mutual positions will be the same, therefore potential, attraction potential, how ions attract electrons will also be the same. So the potential in the cell that is far away will be the same as the potential of attracting between nucleus and electrons in the parent cell. Parent cell. Okay? There is a theorem that tells how this property of potential reflects on the properties of electronic wave function. I was going to plot it myself again, but let me show you just all plotting. So potential means that at each nuclei you have attractive potential. If you want to let electrons to sit in this periodic system, of course they will sit above this this set. Here, there, and there. But you can imagine, from especially those of you who took physical chemistry, that if there is an infinite periodic cell, there are solutions of plane waves that travel with non-zero velocity, travels through another cell, and by moving forward in time and space, the wave function accumulates phase. So if you compare part of wave function at each of the unit cells, the shape of the electron density will be the same, but in addition, it will accumulate phase proportional to the distance to this cell. So number of unit cell vectors times size of this vector. So the phi of R plus NA will be the same as wave function at parent unit cell times exponential times I vector k times NA. So there will be phase factor. Right now it tells us nothing, but later on it will be related to ability of electrons and holes move with specific velocities across the cells. So this property of wave function, the accumulation of phase while moving from one unit cell to another, is referred to Felix Bloch. His name, you will meet his name again when you will deal with, in details, with nuclear magnetic resonance. So he was acting in different directions. And the part that doesn't have phase, the part of the wave, the factor in wave function that refers only to near environment can be called like atomic part, and the part that accumulates while traveling from one unit cell to another is phase. Where in addition to typical index of orbital as we have in molecules, we also need to specify the index of momentum. So it will correspond to pace, velocity, how quick this wave moves through. So there will be a lot of solutions of non-standing waves. In molecule, all waves are standing, all orbitals are standing, and in solids, there are solutions that move. And if you merge together like index of orbital and different set of this momentum, you can call it band. And you already saw this terminology in conduction band, valence band. So it is sourced from solid state. If you have a molecule with just HOMO and LUMO orbital and then nothing, the word band is not quite matching. It's more for very dense bands. Good. Okay. I hope you have a little more patience, especially Christian, because I plan to give him a credit. So you got heads up about specifics of solids, and we will speak of them more and more, because chemistry cannot exist. Even wet chemistry has beakers of solid walls. So there is interaction with surfaces. Right now, a little bit more about observables. Suppose that we have solved Hardy-Fock equations. Suppose that we do have orbitals that match self-consistent field. We have energies of orbitals, and now we need to find total energy. There are contributions to total energy that come from kinetic energy of electrons and their attraction to ions. They are contributing to energies of orbitals. And there is additional terms that come from Coulomb repulsion and exchange stabilizing factor. Right? So total energy includes adding together energies of all occupied molecular orbitals and Coulomb electron-electron interactions of all occupied orbitals. So therefore there are two indices. I'm going to make a big heretical step. Something that you probably shouldn't tell in public. What if we keep only this first simple term and just neglect electron-electron interaction? Suppose that electrons do not interact with each other. You know that it is wrong. Your molecule will just blow away, or you will do something wrong. But just as a little numerical experiment, what if we just drop this term. And these orbital energies come from kinetic and electronuclear interaction. Let's use it just as a working tool to get some qualitative analysis. I didn't declare a goal. It's a wrong style of thinking. We should declare goals every time. So the goal is to compare stability, energetics of neutral molecules, cations, and anions. You know, cation when you remove electron, anion when you contribute electron, and compare their total energies. So if you go from between neutral cation and anion, your highest occupied will change. If it is cation, you have HOMO by one less, just subtract one. If you have anion, you run the summation to higher, more terms. And same for this, but we are dropping. So this is wrong. But formally, it does depend on number of electrons. So if you change number of electrons, total energy will change. This statement is correct. Okay, you recognize this person, and his name is not Coupon, but he contributed to our perception of this theory. So those are occupied, and if you create cation, you remove electron from home. If you create anion, we add electron to home. And then we just agreed on the previous slide that total energy depends on number of electrons. So I'm going to do nothing more than this picture, but in more detailed way. Up, down, 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 up. Up, down, up, down, up, down, up, down, up, down. One more up. So this is neutral. This is cation. This is anion. This is energy of HOMO. This is energy of HOMO plus 1, or energy of HOMO. And this is again energy of HOMO. Right? So if we agree this wrong step, approximate step of dropping electron interaction, then we will obtain total energy as summation of orbital energies of all occupied orbitals, right? Oh, in the past. And you can go ionize it much heavier by adding or removing electrons. So if you have neutral, if you have n electrons, you count energies of first, second, third, and last. If you do cation, you have one less term in the summation. If you have anion, you have one more term in the summation. Right? So if you want to be rigorous in procedure, in results we are already wrong, but if you want to be correct in procedure, the energy of electron ionization energy is energy of cation minus energy of neutral. Okay. So we take this one and subtract this one. This minus this, zeros. This minus this, this minus this, 0. Minus E sub n. Right? proof. It's a proof of Koopman's theorem. So if you drop electron-electron interaction, the ionization energy will be energy of last order. Sounds convincing? So Koopman's theorem means that you drop electron-electron interaction. If you need electron affinity, how do you do it? By the way, if you do not do with Koopman, you just change charge in your model, find total energy and subtract. And this will be much more reliable. Koopman's is just for quick estimate. And if you do this literally, you'll get very reliable results. So you take of n, here's minus 1, n plus 1 minus e sub n. So you subtract this one and this one. E1 minus E1, 0, E2 minus E2, 0, En minus 1, En minus 1, 0, En, 0, you get En plus 1. So energy of LUMO. So energy of LUMO is electron affinity. Convincing? This is. Do you have anything else? Yes. Energy HOMO, energy LUMO, and my favorite slide. Thank you for your patience. So I was debating to collect or leave with you, but probably leave with you your derivations. So the equation for matrix element of transition dipole for optically induced transition is something that is you shouldn't be ashamed to put in the methodology of your research papers. Okay, I'll stay here to answer any questions, but meeting is done.